Alright, so in this video I'm going to go over the cost analysis on this part right here you see in the upper right hand corner. I'm going to detail the cost difference between milling that part or turning that part. So in the previous videos we looked at this milling fixture right here. We went through all the operations that would happen, and then we also went through what would happen if we turned a part on a lathe with a bar stock. But this part of the video is actually just going to be detailing the different costs and basically breaking down everything that would have to go into it. So basically the way this sheet works is top to bottom we just start adding costs, and adding costs, and then at the end there's a summary showing the difference. So I'm just going to go through line by line and explain my thought process through each of these sections. So for fixturing right away, we have an advantage for turning because if you have a lathe that's set up, all you really have is the chuck. There's no additional fixturing needed. With the milling, we needed 3 Pearson pallets, vacuum pallets. You need the bases for those pallets, you need the connection kit, and you need the clamps to clamp all your material down. So that's for this. And then for turning, we have 0 fixturing cost. So if we keep going, tooling list. So for the mill is on the left. We have a 1/2 inch end mill, 1/4 inch end mill, slitting saw, a drill, and a tap. And then for turning, we have an additional tool. We have 1/2 inch carbide end mill, slitting saw, drill and tap just like before, but then we have the addition of a CNMG carbide insert and the cutoff insert for parting the tool off, for parting the part off. So we have similar prices at the end, tooling costs. So here this goes into the basically tool life expectation of the tools, and I'll break this down for you. But basically what I used is I found this peer-reviewed article, and it gave we're cutting 300 series stainless steel, so this basically correlates the cutting speed to the tool life. So that's what I use for my calculations. So we'll start on the milling. So we have operation 1, operation 2, operation 3. This is the time in the cut. This is not the machining time that the machine will take to run. This is just the time that the actual cutting tool is inside contacting the part. So basically this is the time that the cutting tool is being worn down. So the total time per part is 2.92 minutes. All these figures are in minutes. So we take a tool life of 30 minutes based on our calculations that we found online, and the link is right here. So the total time in cut per part is 2.92 minutes. So that is basically one tool can turn out 10.28 parts. So you're going to get about 10 parts per tool. The number of tools is 5. The tool cost total was $218, so then I averaged that out. So you're spending about $43.80 per tool. And if you're spending that much money per tool and you have this many parts per tool, then let's see the formula I use. Yeah, you just divide those, and then you get, it costs about $4.26 per part in tooling. So you're going to spend $4.26 for basically one part just for the tool wear that's going to occur. And then I multiplied that out for the parts we're expecting to do in a year. So you can see I did 1,250 parts times 52 weeks, because we're expecting 1,250 parts per week, 52 weeks in a year, times that value. So then if we go over here to the turning side, similar. So on the turning side, we have a live tooling, which is actually milling. So there's a combination of milling and turning going on. 3 operations of each, so we average it out. 22 minutes is the average tool life for turning. 30 minutes is the average tool life for milling. So we just average that out to 26 minutes average tool life. The time in cut is a little bit less, so we're actually going to get around 11 parts per tool instead of 10. The number of tools is 6, total cost 230, so the average tool cost is 38 compared to 43. So then when we calculate all that out, we're looking at a little bit less, $3.52 cost in tooling per part. So that's $276,000 per year compared to $228,000 per year. So it's definitely some savings. It's not crazy, but it's pretty substantial. And then here is just the output of Fusion 360. So it gives you your feed time. Feed time is time in the cut. And then machining time, which is, it includes your rapids and your tool changes and all that, because tool changes take time. So now we're doing parts produced per week per basically method. So with milling, we have to consider the fact that an operator is going to have to stand in front of that machine and change out the pallets. And then once that pallet finishes, once those 3 pallets finish, an operator has to be there to put in the other pallets. Whereas with the lathe, since it has an automatic bar feeder, basically as long as the machine is stocked up with bar stock and you have enough tools in the machine to keep running, that machine can run through the entire week unattended, just with somebody there for maintenance. So I assumed during a 7-day week, I assumed that the machine would be running 60% of the time. So that's basically just assuming that somebody is stocking up the bar feeder, somebody is making sure the tools are replaced. Obviously there's going to be downtime for replacing tools. There's going to be some downtime for loading additional stock. That there's going to be downtime for maintenance. So that's why I picked a value of 60%, which is pretty conservative. Some shops would easily push that up to 70-80%. But let's start from the top, from the bottom over here on the left side with milling. So we have our machining time. This is the time that includes tool changes and rapids for traversing to the tool. This isn't in the cut time. This is total machining time. So total machining time per part adds up to be 4.2 minutes. We're machining 48 parts per cycle because there's 16 parts in one pallet and there's 3 pallets. So that's 48 parts that we have to machine in one full machine cycle. That adds up to about 202 minutes. You're machining, this is the time it would take to finish machining those 3 different pallets inside the machine. So you're machining 3 pallets, but you're only actually finishing 16 parts per cycle. So, you have the first op and the second op. Those aren't finished parts. Only the third op is finished. So then we go down to here. Your standard shift is going to be 480 minutes. That's 8 hours times 60 minutes. So this is how many cycles we're going to get per shift. So if the total machining time per cycle is 201 and we only have 480 minutes in the day, then we're going to get about two pallet changes and then one at the end, because they're going to let one run overnight. So you get one. Basically, the operator comes in at the beginning of the day. They start up the machine, that's 1. And then in the middle of the day, they change to the second one, that's 2. And then after that one finishes, so after about 400 minutes, they still have 80 minutes left in the day, and then they put another one on. So that rounds up to 3 effective cycles per work shift. And remember, you're getting 16 parts per cycle. So that's 48 effective parts per shift. So one guy working 8 hours, 40 hours a work week, he is putting out 48 parts on one machine. So here we have basically 48 multiplied times 5 days. We're a 5-day work week. And then we say, okay, well, what if we work 2 shifts, 480 parts a week? What if we work 3 shifts? That's 720 parts per week. So then we multiply that times 2. That's 1,440. So that's a good margin above 1,250, because we want a little wiggle room. If one machine goes down and we have to fix it or whatever, we want to be a couple hundred parts above our goal, just so we have some wiggle room. So basically the conclusion is that you would need 2 mills running 3 shifts on a standard 5-day work week to meet the quota of 1,250 parts per week with this current fixturing setup. And you could try to put more parts on that mill. You could try, but I mean, we're already at 3 full cycles per work shift, so even if you add a couple extra parts, you're going to get diminishing returns. But now let's go ahead and look over at the turning section. So your machining time is 3.9 minutes, so about 4 minutes per part. And then it's pretty simple here because, you just get one part per 3.9 minutes. And then you look at how many parts you can get a week. So this is how many minutes are in a 7-day week. This is multiplied times 0.6 because we're assuming the machine uptime is going to be 60% of a 7-day week. I'm using 7 days instead of 5 days because remember that this machine can run unattended. So Saturday and Sunday, it's probably not going to run Sunday, but it's probably going to run quite a bit into Saturday because the machine will be stocked up with fresh inserts and bar stock on Friday so that it can run through into the next day. And that's part of that 0.6 figure is we're figuring it's going to run 60% of the 7 days. And then this is basically we divide this and the machine time parts per cycle. So you can see we have 6,048 minutes to machine in a week, and our BART takes 3.9 minutes. Divide those out, and we're looking about 1,500 parts per week. So similar to this. So we're using one lathe, one shift. So there's only one person that needs to attend this, and the person is only working 5 days a week, but the machine is actually going to run at around 6 days a week. And you're getting around the same output. And this is only with one machine. Keep in mind, this is with 2 machines. So 2 machines and 3 shifts compared to 1 machine and 1 shift. And that's about the same output. So it's kind of crazy how much more efficient this automated lathe can be. And now we get into the labor costs where, it really shows how much effort it's going to take to load this mill compared to the lathe. So on the left, we're just going to start with a standard $20 an hour rate for a machine operator. In rural areas, it might be less than 20. In cities, it might be more than 20, but we're just going to pick a nice number, which is 20. So it's an 8-hour work shift, 5-day work week, 840 basic. So we need 3 shifts, and we need 2 operators because we're running 2 different mills. The cost of one shift, the cost of one worker for one shift for a whole week, 5 days, $800. The cost of a worker for 3 shifts of a whole week. So that's basically 3 people per day because it's 3 shifts for a whole week. It's $2,400. And then the cost of 2 workers for 3 shifts for a whole week. So basically that's 2 machines running, 3 shifts a day, 5-day work week. That's $4,800. And then if we take that and multiply it out across the whole year, it's about $250,000 a year in labor to keep those 2 mills running for 3 shifts for the whole year. We go over to the right here, same base pay rate. We're only working 5 days a week, 8 hours. Cost of one worker for a whole week is $800. But since it's only one worker, and it's only one shift for the whole year, it's only $42,000 instead of $250,000. So quite a bit of savings there. Now we'll go on to material, where we get a little more savings. So for a 6-foot square stock, it's $164. Averages out to about $2.28 per part. $148,000 per year just in materials for that 1,250 part a week figure. Go over to the right side. This is the turning section. Round bar is going to be a little bit cheaper. So we're looking at $112 for a 6-foot stick instead of $164. So that's $1.57 per bar. So that's $101,000 per year compared to the $148. So you're saving about $50,000. And then also something to consider is over here, you're going to have saw cutting fees because you have to cut this stock down to size for every single part. And, a saw cutting outfit is going to charge you I don't know, $1 per cut or whatever it's going to be. I mean, you could do that yourself too, but then you're spending more in labor cost. You do still have to prep the bar stock over here when you're feeding bar into a lathe. You have to chamfer the end so that it feeds into the machine correctly and it doesn't jam. But that's a lot less maintenance than cutting every single piece of square stock. I didn't factor in those costs because, it's kind of a wash. It's not going to have that much cost, but it's just something to consider. It's another plus for the lathe side. So now basically at the end here, I'm adding it all up. So we had the fixturing cost up top. That was only $8,000, but keep in mind we're doing 2 machines, so we're doubling that, so it's $16,000. Tooling cost per year, $276. Basically, this is all the figures we just looked at, but added up. And then at the end, we have a flat rate of machine setup time, programming, and engineering time. That's basically just to kick off the project. Over here, we're looking at $700,000 the first year, and then these costs right here are not reoccurring. These are one-time costs. One-time cost for the fixturing, one-time cost for the machine setup and all that. So basically the reoccurring cost per year is $675,000. We go over to the right and you can see it's not quite half, but it's almost half. So because the machine is automated, you're spending almost half the time. I mean that's you're saving time in almost every single category, or you're saving money. Your material cost is less because you're using round bar. Your labor cost is almost like a third or a quarter. And then your tooling cost is also a little bit cheaper because turning inserts are just always going to be cheaper than end mills. Also, turning inserts are indexable, so you can turn them around and use the different faces, whereas an end mill is not indexable. Once it's done, it's done. And then you have no fixturing cost. So you can see obviously the recommendation to this customer would be, we want you guys to use the turning method because it's going to be super cheap. Now, if you were a small company and all you had is a mill and you didn't have a lathe, it wouldn't hurt to use a mill, but this is where actually calculating out the long-term benefits can be really helpful, because if you were a company using a mill to make these parts for a whole year, you would be losing, I don't know, almost $300,000 because you could have used a better machine for the same job. Also, I didn't calculate in the cost of the machines, but if we just say a mill, I mean, even if the lathe is 2 times more expensive than a mill, it still makes sense to go with the lathe. Like, let's say the lathe is, I don't know, $150,000, and let's say the mills are, I don't know, $100,000 for 2. If you're using an old VF2 mill, and you have 2 of them, and they're $100,000 compared to buying a brand new single $150,000 machine, I mean, it's hard to beat the savings. The savings in time, the lathe is not going to be prohibitively expensive enough to not make it worth it, is basically what I'm saying. So even though this machine is more expensive, the lathe is going to be more expensive. It's still going to be worth it. But yeah, that's the breakdown of the cost summary for each of these methods. So I hope that made this clear. Thank you.